So we're going to talk about three different limits in this video. One of them we can do a lot like the limits we did in Calc 1, and the other two, we're going to use some more advanced techniques. So first we have the limit as xy approaches 0, 0 of x to the fourth minus y to the fourth over x squared plus y squared. And kind of our bread and butter in Calc 1 was to kind of simplify and cancel things until we got something that is defined at the point we're interested in. So again, if you plug in 0, 0, you'll get 0 over 0 undefined. But we can do a little bit of simplification here. I'm just going to write limit. I'm not going to remind us what we're approaching just for the sake of time. But I know that I can factor the numerator into x squared plus y squared times x squared minus y squared over x squared plus y squared. And we get some lovely cancellation going on. We get the limit of, I'll write it again, xy goes to 0, 0 of x squared minus y squared. That's just going to be 0 minus 0 because now we can plug things in and we get 0. So that feels like a Calc 1 type of limit. When we get to the next problem, we run into the problem that we can't factor. That's a problem. But we do have a tool at our disposal. We're interested in what happens to f of x, and x being a vector, as the vector x gets close to 0. And you know what? I will write it as xy. What do we mean by xy gets close to 0? We're saying what happens to the magnitude. I'll write it out. What happens as the magnitude of xy gets close to 0? Or the square root of x squared plus y squared gets close to 0. Well, we have another way of writing the point xy in polar coordinates. Where r is the distance of our point from 0, so r is the square root of x squared plus y squared, and theta is, well, we know that the tangent of theta equals y over x when x is non-zero, and that there's some other shenanigans involved there. But what that tells me is that I'm really interested in what happens as r goes to 0. And that just has one variable I'm interested in. Sure, we have a theta poking around its head, but hopefully, no matter what theta is, the limit should just depend on r in some way. And if the limit as r goes to 0, it gives me a unique value no matter what theta is, then we're in business. So what we can do is we can convert this to polar coordinates. This will be the limit as r approaches 0 of, well, what's x? X is going to be r cosine of theta to the fourth. So we'll have r to the fourth cosine to the fourth of theta, plus y to the fourth is going to be r to the fourth sine to the fourth of theta over x squared plus y squared is just r squared. So this is going to be the limit as r goes to 0 of, we can cancel out some r's. We'll have r squared cosine, and we can actually factor out some r's too. So this will be r squared cosine to the fourth theta plus sine to the fourth theta. And I don't know what cosine to the fourth theta and sine to the fourth theta are. It could be, theta could be anything. But what I do know is that 0 is less than r squared cosine to the fourth theta plus sine to the fourth theta, which is less than, should put a less than or equal to, which is less than at least 2r squared, because each of these things can only be at most 1. And I know the limit as r approaches 0 of a couple of these things. This limit as 2r squared goes to 0, of 2r squared as r goes to 0 is 0. The limit as r goes to 0 of just the constant 0 is 0. So that means that this limit here that we're interested in is going to equal 0. And that's exactly the limit that we were trying to solve at the beginning, so lo and behold, we have calculated our limit. So let's look at the case where we have 3 variables, and unfortunately, polar coordinates don't work for 3 variables, but there is another coordinate system that has a component that represents the distance from the origin. And that is spherical coordinates. So I should mention at this point, all of this is working out nicely because we're interested in the distance from the origin. And polar coordinates have r, which represents the distance from the origin, and spherical coordinates have rho, which represents the distance from origin. So if we're approaching a different value, then we'd have to be a little bit more sneaky in how we used these approaches. And it would probably be a whole deal. So we're probably not going to do that. So let's go ahead and use spherical coordinates. So what you might remember, maybe, is that x is going to equal rho sine of phi. Phi is the angle it makes with the z-axis. Cosine of theta, that's kind of the amount we rotate around the z-axis. Y equals rho sine of phi cosine of phi, of theta. And then z just equals rho cosine of theta. So if we convert this over, we're going to get the limit as rho goes to 0 of rho cubed cosine, rho cubed sine cubed of phi cosine cubed of theta plus r rho, that's a rho, not an r, rho squared sine squared of phi and cosine squared of phi. Let's make those signs because they're supposed to be. That's sine of theta. That's going to be sine squared of theta. All of that over, well, x squared plus y squared plus z squared is just rho squared. I can cancel out some of my rho's, but not all of them. So I'll have the limit as rho goes to 0 of rho times sine cubed of phi times cosine cubed of theta plus sine squared of phi sine squared of theta. And for reasons similar to what we did before with the squeeze theorem, this first part's going to go to 0. So that goes to 0. So this is going to be the limit as rho goes to 0 of sine squared of phi sine squared of theta. And here's the problem. Because with what we're left with, we don't really know what this value is. This could be anything. Anything from 0 to 1. I'll write some interval notation. Depending on the values of phi and, actually it's some square brackets too. Let's do that. Okay. depending on the values of phi and theta. So since we don't get a unique answer, we would say the limit does not exist, because we don't know what's happening to phi or theta. We can pick whatever we want for those. So the limit doesn't exist, sad day. If we had been able to do the same type of squeeze theorem thing we did back there, we would be able to say that yes, this limit does exist, and here's why. So there are some examples of using various coordinate systems and different techniques to calculate limits in multivariable functions.